In the 17th century, motion was described using forces. This was the world of Isaac Newton. Newton's famous equation, F equals ma, became the foundation of classical mechanics. But 2 centuries later, physicists discovered something deeper, a completely different way to describe motion. Instead of forces, nature seems to choose paths that minimize something called action. This idea led to one of the most powerful equations ever discovered, the Euler-Lagrange equation. This equation governs planetary motion, pendulums, electromagnetic fields, quantum mechanics, even modern particle physics. It is used everywhere in modern theoretical physics, from spacecraft trajectories to quantum field theory. And today we are going to derive it from the very beginning. Before we talk about physics, consider a simple problem. You want to travel between 2 points. What path will you take? Usually the shortest distance, a straight line. Mathematically, this means nature is solving an optimization problem. It chooses the path that minimizes a quantity. In physics, that quantity is called action. What is action? Action is defined as the integral of something called the Lagrangian. The Lagrangian is written as L equals T minus V, where T kinetic energy, V equals potential energy. This concept was developed by the mathematician, Joseph Louis Lagrange. Now we define action. Nature selects the path that makes the action stationary. Not necessarily minimum, but stationary. This is called the principle of least action. It was explored deeply by Leonhard Euler and later by William Rowan Hamilton. Suppose a particle moves along a path of 4. The action depends on that path. Here, x is position and x dot is velocity. Now imagine slightly changing the path. We introduce a small variation, where epsilon is very small. The function eta t represents a small deviation in the path. The action becomes. If the true path minimizes the action, then ds by d epsilon equals 0, where epsilon equals 0. Now we expand using calculus. Taking the derivative inside the integral gives naught. Now we simplify this expression. The second term contains eta dot. To eliminate it, we use integration by parts. Integration by parts gives. The boundary term disappears because the endpoint of the path are fixed, so the variation becomes. For the action to be stationary, the variation must be 0. Delta S equals 0. Since eta t is arbitrary, the only way this integral can vanish is if the term inside the parentheses is 0, which gives the Euler-Lagrange equation. This is one of the most powerful equations in physics. Let's test it. Take a simple system, a particle with a mass m moving in a potential v of x. Kinetic energy is? So Lagrangian is re? So compute the derivatives. First, delta L by delta x dot equals mx dot q. Then d by dt mx dot equals mx dot. Next, delta L by delta x equal minus dv by dx. Substituting into the Euler-Lagrange equation gives mx dot equal minus dv by dx, which is exactly Newton's second law. Why physicists prefer this form? Because the Euler-Lagrange equation has enormous advantages. It works for complicated coordinate systems, rotating systems, constraints motion, fields, relativity, quantum mechanics. Instead of forces, we only need the energy of the system. This makes it extremely powerful. The same equation appears everywhere in modern physics. It is used to derive Maxwell's equations of electromagnetism, Einstein's field equations in relativity, the equations of quantum field theory. For example, the standard model of particle physics is essentially a massive Lagrangian. Every particle interaction emerges from applying the Euler-Lagrange equation. The Euler-Lagrange equation reveals something profound. Nature does not think in terms of forces. Nature thinks in terms of paths through time. Among all possible paths, the universe selects the one that makes the action stationary. Every orbit, every wave, every particle, all follow this principle. From planetary motion to spacecraft trajectories to the deepest theories of reality, one equation quietly governs them all. The Euler-Lagrange equation. A single mathematical rule describing how the universe evolves. And astonishingly, it emerges from a simple idea. that nature always chooses the most elegant path.